Hello everyone. Today I'm going to talk about an automated framework for image classification and segmentation of fetal ultrasound images for gestational age estimation. I am Juan Carlos Prieto and my collaborators are Hina Shah, Alan Rosenbaum, Xiaoning Yang, Patrick Musonda, Joan Price, Elizabeth Stringer, Bellington Valika, David Stamilo, and Jeffrey Stringer. This research is done at the University of North Carolina with support of the Bill and Melinda Gates Foundation, and some of my collaborators are from the North Carolina State University. This is the Ultrasound Fetal Age Machine Learning Initiative, US FAMLI. So, to introduce this subject, the primary purpose of this research is to automate the identification of fetal structures in ultrasound images. We want to be able, primarily, to predict the gestational age, and by identifying also these fetal structures, we hope that we can identify anomalies, complicated or high-risk pregnancies. Gestational age is crucial for the decision-making of medical care for baby and mother, and is done through ultrasound imaging in the first trimester. This is the gold standard. By automating all of this process, we hope to improve access to healthcare in remote or rural regions in the world. Preterm birth is the leading cause of death. 1 million children die each year from this condition, or they may face a lifetime of challenges, learning disabilities, visual and or hearing problems. So by improving the access to healthcare, we hope to reduce all of this. Here we can see some statistics on maternal mortality in a study done in 2007. As you can see here, industrialized countries have a much less rate of maternal mortality than developing regions in the world. The divide is quite clear between industrialized and developing regions in the world. There is greater maternal mortality, there are more complications related to the pregnancy and childbirth, and it's almost 300 times greater. So this is one of the things we want to tackle by developing technology. Here we have also rates of neonatal mortality, which, as we can see here, is much higher in developing regions in the world than in industrialized countries. So, the outline of my presentations: first, I'm going to talk about the datasets, all the datasets that we have to train our deep learning algorithms. The issue is that historic image datasets, they contain calipers. They may contain measurement tags or markers that have been put by expert sonographers. These markers or tags will render these images unusable to train neural networks, because a neural network will learn to identify these easily. So first I'm going to talk about the caliper, so a technique to remove these calipers, remove tags or text from the images. Then I'm going to talk about what classification approach we use to categorize these images into our different classes, so head, femur, abdomen, or fetus, or crown rump length. These images will allow us to predict gestational age. We will talk about a segmentation method to identify the regions of interest in these images, and a method to fit different elements, for example an ellipse or a circle or a line, according to the structure. And then we will use these fitted elements to measure the structures and then be able to do gestational age prediction. So this is an overview of our pipeline. I will talk about the images that we have in our dataset. Then I will talk about our caliper removal technique, which will basically take as input any type of these images and produce a raw ultrasound. Then this image is classified into their respective category. Once it's classified, we will segment the image and then fit an element to it. And once we have fitted the element, we will proceed to measure the structure, and then using the Hatlog formula, we can predict the gestational age. So let's first talk about our datasets. So we have a vast dataset retrospective that has been acquired at the University of North Carolina as clinical routine care. We have 2,900 sessions with 124,000 images from dates from 2012 and to 2018. These images will have calipers present in them, and we will use these images for training and validation. We have another dataset, our SAPS dataset, prospective cohort from Zambia, acquired in University Hospital in Lusaka, Zambia. We have 3,300 sessions with 23,200 images from days from 2015 to 2017. They have calipers in them, and these images are used for training and validation. And finally, we have our fetal age machine learning initiative dataset, prospective cohort, acquired in Zambia and North Carolina, with 2,400 sessions, 7,200 images, dates from 2018 to 2019. They do not have calipers in them, and we will use these images purely for evaluation. So here are some examples of the images in our SAPS dataset, which, as you can see here, have different types of calipers in the image and have different types of text and measurements in them. Here is an example of our UNC routine care images, which, as you can see as well, it has some text or different types of calipers in the image. So we want to be able to remove those because a neural network we will learn to identify them easily. Now let's talk about our caliper removal technique. So we generate our ground truth data using an in-painting or texture synthesis technique. We first detect our caliper region, and we replace this region using an in-painting technique. And in general terms, how this works is we have this detected region, and we want to replace the pixels in them by finding closest neighbors or redundant information in the image, and we will average the pixel in the region by all the closest neighbors. And this way we can basically remove patches from the image. And so these images are used as ground truth for to train a neural network that will be able to remove calipers or annotations automatically. We also alter the input images for this step by adding different types of calipers, the small ones, the big ones, and different types of letters in the image by adding them randomly. So what is the so this is a diagram of what we're trying to what we accomplish here. So we have an input image that has random calipers in them. We use the images generated by the in-paint technique as our target, and we train a unit architecture. And we minimize the mean squared error in this task. So what do we accomplish with this? So we have a unit, a trained model that can take as input any type of image, and it produces a raw ultrasound images at the other end. And we do not need to identify any of the region that has the calipers. This is done automatically by this approach. So, and these are the results of this step. So we have an image, and if we input into this network, this is the output that we get. We get a raw ultrasound at the other end. So this step can be seen as a denoising step to remove any type of artifact in the image, and it produces raw ultrasound. So now these images can be used for training deep learning algorithms. Now let's talk about our classification. So we train a residual network with 50 layers. So it's a deep residual network. This type of network addresses issues with the vanishing gradient by adding this these shortcut connections, feed-forward shortcut connections. And this is one block of our residual network that is composed by convolutional operations. And these are the result of our classification. So this is on our validation set. So we split our data 80% for training, 20% for validation, and as we can see here, so we have high accuracy around 90%. And this is our result in our evaluation dataset that does not contain any calipers or text. So as we can see here, the classification is even much higher even. So this means that maybe our dataset this dataset is working much better in our evaluation dataset. Now once we have classified all of our images, then we can proceed to segmentation and measurement of the structures of interest. So here we will talk about how we generate our ground truth. So we generate label maps using the position of the calipers, and we train a neural network to detect and output a label map of this region. Again, for this task we use a unit, but we're instead trying to optimize for the intersection over union metric. So our ground truth is generated by detecting the position of the calipers, and then we generate, for example, for the heads, we generate an ellipse. For our abdomen, we detect the position of the calipers and we generate a circle, or for our femurs, we generate a line in the region. And these are the results for our segmentation approach. So we find that our metric is high for the detection of heads, is 0.95. For our abdomen, it's 0.9 on average. For our femurs, it's 0.89. Now once we have detected our region of interest, we proceed to measure it. So the output of the segmentation, we can use it to measurement and prediction of gestational age, because we can basically fit a circle, or ellipse, or a line to the resulting segmentation, and then we can use these to produce our measurement. So this is our approach for ellipse or circle fitting. We are trying to find an angle, minor radius, major radius, and then the center of the circle. And for a line fitting, we are again trying to find the 2 points that describe this line. So this is the result. So this is the result of our output segmentation, and then to this region we will fit our ellipse. So based on the resulting region. This is for our abdomen. So we fit a circle to the output region. This is for our femur. We fit a line to the region. And this is once we have fitted those elements, we can proceed to measurement. And this error here is in centimeters. So for our validation dataset, we find that the biparietal diameter, a mean error of 0.8, and in our evaluation dataset, we find that it's 0.4 error with 0.5 in standard deviation. Our head circumference 2.9, and in our evaluation dataset is 1.0 centimeters. For abdominal circumference, mean error of 3 in our validation dataset, and 2.27 in our evaluation dataset. 0.7 mean error in our validation, and 0.5 in our evaluation dataset. So, in conclusion, we have an algorithm that can remove calipers from ultrasound images. These images can be used to train deep learning algorithms. We have a vast amount of data that can be used. We have a fully automated framework for classification, segmentation, and measurement of fetal structures of interest. We have tested all of this approach in images that do not contain any tags or calipers. We have 716 sessions that had all the measurements, and we compute the gestational age using the Hatlog formula, and the mean error was 1.4 days. As future work, we want our framework to not use these images that are acquired by experts, and we want to be able to identify these fetal structures using purely blind sweeps. Thank you very much for your attention.